Hello dear friends, welcome my channels. Today's discussions is group theory problem solving. So friends, my first problem is number A. The number of element is z11x x square plus 1. So friends, this type of questions formula is if general formula. I write general formula. General formula is Zn x divided by x to the power m plus 1 plus a x to the power m minus 1 up to c. This type of problem we get n to the power m. We get m to the power m. So n is in here 11. So it is 11 square. Another is 2. So we get 2 to the power 4. 11 square is equal to 121 and 2 to the power 4 is 16, and here just multiply, just adding 3 plus 2, so we get 2 to the power 5 equals to 32. So this is my answer. My answer is 121, 16 and 32. Next problem friends. Which of the following rings are PID? Number 1, QX, ZX, Z6ZX and Z7ZX. Now you see that Q is a field. Q is a field, so QX is ED, that is it tends to PID. So this is PID. And ZX, friends, Z is not a field. Z is not field. So ZX is not PID. So number 2 is wrong. Number 3, that Z by PZ isomorphic to ZP. If P is prime, then ZP is field. So friends, here 6 is not prime, so it is not PID, but this portion is 7 is prime, so Z by 7ZX is PID. Field means PID, and field means that implies PID, principal ideal domain. Next problem. Consider the group G comma dot and 1 minus 1 G. This is cyclic or not? So friends, definition of cyclic group. If G equals to A and B a finite cyclic, be a finite cyclic group, then order of G equals to G. Order of G equals to order of A. Cyclic group, then order of A. So friends, you see that order of G is equal to 4 and order of -1 equals to 2, order of 1 equals to 2. But when you see order of I, that is 4, or order of -I equals to 4. So friends, we see that therefore order of I equals to order of G, hence it is cyclic. Because group has a generator, group has a generator. Next questions is based on simple group. G be a simple group of order 60. What is the G has simple group of order 60 means that is G normalizer group is only G or E or and E. So we can get only two groups, G and E, from a simple group. Now whatever you see friends, you see that G has 6 silo 5 group. This is true or not? Silo third groups, silo third rule. Silo third rule, NP is equal to 1 plus Kp. NP is equal to 1 plus Kp, where K is equal to 0, 1, 2, 3, etc. So whatever you see, 60 can be written 1 into 2 square into 5 into 3. This way 6 can be written, and P equals to let. So let P is equal to 5. So P is equal to 5. So 1 plus N5 is equal to 1 plus 5K divided by 12. Then K is equal to 0 is divisible by K is equal to 1. And when K is equal to 1, so NP is equal to, we see NP is equal to 6. So we get 6 silo 5 subgroups. K is equal to 0, K is equal to 0, then NP, N5, NP means 5, N5 is equal to 1. So it is not correct. This portion is not correct because that means normal subgroup. Normal subgroup. It takes normal subgroup. So okay friends, so this portion is correct. And after that, G has 3 silo subgroup. Again we see 1 plus 3k divided by 20. Then if we put the value k equals to 0, k equals to 0, so N3 equals to 1. That is not possible. If k equals to 1, so we get 4, and 4 divisible by 20. But in case of k equals to 1, when you see k equals to 1, then 4 divisible by 20. But N3 is normal subgroup, as 4 does not divisible by 10. 4 does not divisible by 10. So whatever you see that G has 4 silo 3 subgroup is not possible. G has cyclic subgroup of order 6. So friends, we can take a counter example that which is simple, that is A3. G is isomorphic to A5. G is isomorphic to A5, as order of A5 is equal to 60. Whatever you see that k is equal to 1, 4 divisible by 20. Okay, so we have then if N3 equals to 4, then we have 8 elements of order 8 elements of order 3, and A5 has 20 elements of order 3. A5 has 20 element of order 3. So N3 is equal to, that is N3 is equal to 10. So our second option so our third option is wrong. G has cyclic subgroup of order 6. Sorry, 4 cyclic subgroup of order 6. This is also wrong. And G has cyclic subgroup of order 6. This is also wrong. This is wrong because suppose h is equal to order of h equals to 6, it can be written 2 into 3, 2 into 3, so therefore k mod of k is equal to 2 and mod of n is equal to 3 and mod of kn is equal to 6. So k and n both should be k and n both, not both should be or not k n. We can say that k and n one should be normalizer, normal subgroup. But as 60 is simple group of 60, so it is not possible. And number D is not also possible because G has unique element of order 2 is not possible, because suppose x zg is equal to 1 as the simple group and x is equal to 2 means it is abelian. X is equal to 2 belongs to zg, and we know that abelian group x equals to 2 means it is abelian. So zg is abelian, but order of zg is equal to 1, so it is contradictions. So friends, our only one answer is 1. Only one exam is correct. Number 5. Number 5 is very interesting problem. That is, let G be a subgroup of order 20. You will see that yes, G be a group of order 20 in which the conjugacy classes have size 1, 4, 5, 5. So order of G is equal to 1 plus 4 plus 5 plus 5 plus 5. You see, is equal to 20. And also they say, then which of the following is true? G contains normal subgroup of order 5 or not. Now you see that n5 is equal to 1 plus 5k divisible by 20 can be written 2 square into 5 divided by 4. So only possible if k is equal to 0, then n5 equals to 1 and it is unique. By third theory. So n5 is equal to 1 is unique, then it has a normal so G is normal subgroup. Number B, G contains non-normal subgroup of order 5. That is totally wrong. It is not possible. Second, G contains subgroup of order 10. Let the subgroup H is subgroup of, let H be subgroup of G. So order of H is equal to 10. It can be written 2 into 5. So let order of K and order of N, K equals to 2 and N equals to 5, and Kn is also subgroup of G, as N is normal subgroup. This is the property of normal subgroup. So friends, whatever you see, N is normal subgroup. So my C option is correct. Now, whatever you see, that order of CLA equals to order of G divided by order of CA, and let order of CLA is equal to size of conjugacy class of A, and order of G is equal to 20. Order of G equals to 20, and order of CA is order of centralizer of A. Order of centralizer of A. So if it is 5, then it is 4. And centralizer is normal subgroup, is not the group. This is centralizer is normal subgroup, normal in the normalizer. Centralizer is normal in the normalizer, but need not to be normal in G. So friends, whatever you see, that G contains normal subgroup of order 4. This is wrong. Another way, friends, if you will see N4 CLO, then 1 plus 4k divided by 1 plus 4k divided by 5. If it is possible, if k equals to 0 and k equals to 1. So possible valuations is as the size of conjugations. We see that if N4 is equal to 1, 0, this is 1, but it is not possible. It is not possible. So possible value is N4 is equal to 5. So 5. So friends, that is, it is not normal subgroup of order. G contains a normal subgroup of order 4 is not possible. So our possible and only answer is correct. Two portion, one is this, another is this. Now we see, let G be a subgroup of GL2R generated by 0, 1, 0, 0, 1 and minus 1. Then the order of G is, how can we find, friends? Because we get 1 is A is equal to 0, 1, 0. If we multiply A square, that is 0, 1, 0 into 0, 1, 1, 0, and this way then we get 1, because it is 0 into 0 into 1, 1, after the 0 into 0, which is 0, and 0 into 1, 0 into 0, 0, 0 into 1 into 0, 0 into 0, that is 1. Then we get this value. So it is I, identity. Similarly, B is equal to 0, 1, minus 1, minus 1, and if we multiply, if we see that B cube multiplying rules, then 0, 1, minus 1, minus 1, sorry friends, this is this way, 1, 0, 0, 1, that is identity element. So friends, whatever we get, order of G is equal to 2 into 3 equals to 6. It is, G is dihedral group. Dihedral group, and elements are, order of G elements are A, comma A square, B, comma B square into B cube, and AB square, this is our total element. Number 7. Now we move. Now we will solve number 7. Z equals to e to the power 2 pi I divided by 7. whatever see that z equals to 2 pi I divided by 7 and theta equals to z plus z square plus z to the power 4, as z to the power 7 equals to 1. So what we get, friends? We see that z minus 1 into 1 plus z square plus z cube plus z to the power 4 plus z to the power 5 plus z to the power 6 equals to 0. We get this value, friends, and after that we get z to the power 6 equals to 1 by z, and z to the power whole cube is equal to 1 by z to the power 4. Similarly, z to the power 5 equals to 1 by z square. Now z into z bar equals to 1. This is the another problem, another factor. So z bar equals to 1 by z. Now we see that theta is equal to this value. So theta bar equals to z bar plus z square bar plus z to the power 4 bar. That value is 1 by z plus 1 by z square plus 1 by z to the power 4, and we get that this value is 1 by z is equal to z to the power 6 z cube z to the power 5 and z cube. This is the total value. Now theta plus theta bar equals to z plus z square plus z to the power 4 plus z to the power 6 plus z to the power 5 plus z cube. So this value is equals to whatever we get this is these equations, either z1 plus z square z cube z to the power 4 z to the power 5 plus z to the power 6 equals to 0. So this value is minus 1, and another value is theta into theta bar. Theta into theta bar is that I will write what is the value of theta. The value of theta is equal to z plus z square plus z to the power 4, and theta bar is z to the power 6 plus z to the power 5 plus z cube. So I multiply this value. So whatever I get z to the power 7, z to the power 8, z to the power 10, z to the power 6, z to the power 7, z to the power 9, plus z to the power 4 plus z to the power 5 plus z to the power 7. So this value is equal to 1 plus z plus z square plus z to the power 6 plus 1 plus z to the power 9 plus z to the power square z to the power 4 plus z to the power 5 plus 1. So this value is 3 minus 1 equals to 2. 3 minus 1 equals to 2. So friends, we get a equation. Now we will solve that. Our quadratic equation is x square minus theta plus theta bar x plus theta into theta bar equals to 0, and x square minus of minus 1 x plus 2 equals to 0. So x square plus x plus 2 equals to 0. That implies x is equal to minus half plus minus root over minus 7 divided by 2 belongs to q minus root over 7. So in here d less than 0. So my option 3 is correct. Option 3 is correct. We are going to solve next problem. The number of subgroup of Z7, 7 of order 7 is, how can I get? I can get this way: 7 square minus 1 divided by 7 minus 1, that is 48 by 6 is equal to 8. Formula is number of element of 7 of order 7 divided by 7 minus 1. Next problem is very nice problem. For any group G, very conceptual, automorphism G denote that automorphism of group G, then which of the following are true? G is finite, then auto G is also finite. Let's start the definitions of automorphism. What is automorphisms? Let G be a group and if such that G tends to G is called automorphism, is called automorphism automorphism if F is homomorphism that is F into A plus B equals to FA into FB, and F is 1 1 and F is on 2. Very nice problem, friends. So we denote OUT G is the set of automorphism. Automorphism from group. Set of automorphism of group. So friends, the problem is very sweet problem. Now you have to know this is the result. You have to know one result, that automorphism of finite group is finite. Automorphism of finite group is finite. So friends, our first option is 100% correct. And second portion. Second portion is very, very important, friends. We go the second portion. Second portion say whatever's in the second portion say. Second portion is ought Zn n subset of Un. If ought Zn, now automorphism of Z8 is subset of U8, but it is not cyclic, friends. Cyclic. Why it is not cyclic? Because U8 is 1 3 5 7 under cross 8 multiplications. Order is multiplications. So G is cyclic and ought G is cyclic. That is not true. Another factor is if such that Z. Another factor is U8 and X8, and U8, order of U8 is 4. There is no element is ordered. There is no element in order 4. There is no element in order 4. Another factor is f such that z tends to z. So what we can get? We can get fx is equal to x, otherwise minus x. So automorphism of z isomorphic to z2. Automorphism of x isomorphic to z2, and z2 is order of z2 is 2. So whatever we see, that g is infinite, then odd g is infinite, this portion is wrong, as z is infinite but odd z is isomorphic to z2 finite. Another factor is odd g equals to odd h, then g and h are two groups such that g subset of h. So z2. Another factor is odd z3 subset of u3. You see, u3 is 1, 2 cross 8, that, and u3 subset of z2. u3 subset of z2 now whatever you see friends, you see that odd z is equal to z2 and odd and z2 so whatever we get odd z is subset of odd z3, but z does not equals to subset z3. Z is infinite and z3 is finite. So this portion is also wrong, as odd z subset of odd z3, but z does not belongs to h. So friends, I hope I can clear this problem. And next, very simple, I do not show the proof. You have to know the generalizations. Generalizations is n to the power m minus 1, as n b to the power n and a to the power m. So according to formula n to the power m minus 1. So you see that it is m is 5. This formula m is 5 and 2 is n. So whatever we get 2 to the power m. 2 to the power m means 2 to the power 5. 5 minus 1 is equal to 31. So this portion is correct. Another is 2 to the power 4 minus 1 equals to 15. So this portion is correct. So I hope I can solve all the questions. If please give your feedback. Thanks for watching.